So we can start with our second tutorial in Module 2. I have downloaded the text file that contains the scripts that we need for this tutorial, and I'm going to show you how to convert that. So I have already associated a folder, Module 2, with my R section, and I have placed the practice script copy into the folder. I'm going to open it, and you'd notice that I wouldn't be able to run anything. There's no run such a button here, and it's because this is a text file and R doesn't really want to look at it as a script. So I'm going to copy and go here and create an R script and paste all of this information here, and you would see that here at the bottom, now that it's an R script, there's a different piece. If you go to the previous tab, it says text file. So I could have changed that in here to enable the screen to be run, and then I can just press Ctrl S and save that. In any case, we'll start with housekeeping, so make sure that you get your working directory set up properly so that your workspace is associated with the proper working directory. I'm going to ask you to install packages called Ergum. You don't really need it for work, but we're going to be using the data that's associated with the Ergum package, so we're going to go through a few additional things to make sure that that data is available to us, and then we're going to detach that package because we really do not intend to do any graph modeling just yet, but we will be exploring the network data set that's associated with some of the classic tutorials for graph modeling, which basically means you will be able to go straight into that later on your own because it's a similar data set. So just installing it, just reminding you what that does. Install packages takes that and loads it into your computer. It takes a lot of time because my Wi-Fi connection is not really good where I'm right now. So we are going to wait a little bit. Excellent, and then I'm going to run library Ergum, which loads that package. We can check here that my package is loaded, and I'm going to load data from package Ergum. So here it is. There's a lot of data sets. We will be using one of the high school data, so that's a simulated, well, it's a fake data set of high school data associated with some of the studies that have been done in a pretty classic analysis associated with that. So Magnolia High is the name of the high school, or Desert High, and we're going to load Magnolia High School data and also Desert High School. And then we are going to rename them because this is a very long name for a network. So we're going to call Magnolia High School network object because this is what this ultimately is. We're going to call it FMH, and we're going to call Desert High School FDH. So I'm just going to create those here. And we are going to detach Ergum because we don't need that. And we're going to run FMH. Please note that this looks different from what we've done before, and that's because Ergum is associated with the StatNet package. So StatNet, as I have mentioned in the first module, is another package that's commonly used for network analysis. We will just do a few simple things in StatNet, and then we'll convert this StatNet object FMH to an iGraph object and continue working with iGraph. But just quickly, let's plot the Magnolia High School data. So this is what it looks like, and if you have looked closely at the description of the network, you'll see that it has quite a few vertices, so more than 1400, and has almost 1,000 edges. We can also run command summary over this network object in StatNet to learn a lot of different information about the network. So I'm going to go up. So it tells us what it tells us its density, it tells us different attributes that we have. So there is a grade attribute, and it gives us a summary of the grades for the entire network, gives us a count of different races of the students, because this analysis is used on student friendships. So do similar students hang out together? So they looked at different attributes. Again, we see gender. Here we know how many boys and girls, and then it shows us the matrix. So the node 11 is connected to node 238, right? It's a self-reported networks of friendships, if I remember well. We can run the same command over the Desert High School data, see, and maybe we should plot it first really quickly to see whether it's a little bit different. There's a lot of clustering happening, so it's quite an interesting network to look at. But we don't really want to use StatNet at this point for consistency purposes. So we're going to load, and if you probably have to install it first. So you have to install Intergraph, load that on your machine, package, and then after it's installed, you're gonna have to load it, and then you will also have to install iGraph package in case that hasn't taken place. And so by now, what we're going to do is we're going to convert the Desert High School network, this guy here, that's a StatNet object. We're going to convert it into the iGraph object using command as iGraph. That's a command that comes from Intergraph package. So we have a new object called ifdh, so iGraph for Desert High School. And you see this is more familiar. This is similar to what we've done last time, but this is ultimately the same information as we had before for FDH. So I can just plot it again here. Does it? Oh, that's because I had typo. Alright, so this is iGraph needs a bit more information to plot this nicely. There's a lot of capabilities, but you need to specify it. But in any case, we're just going to continue and convert that network into the second one, so the Magnolia High School data, also into an iGraph. So we're running as iGraph command over an FMH, which is Magnolia High School StatNet network object, to create another iGraph object. There are several things we'll be looking at. So if you looked at your nodes, this time, you would know that a lot of the focus in this module is on different social processes within the network. Often these are, when it comes to analysis, associated with dyadic and triadic patterns and processes. So this is the network information for the Desert High School network. Let's look at the previous plot. This is this network. It has 107 nodes for 139 edges. It has a whole bunch of different attributes we may want to look at later. So we want to look at the dyad census for this network. And it tells us that there's 91 mutual dyad. You can check what that means in your notes, and you can see these are directed, right? People reported somebody else as their friend. You have 257 asymmetric dyads, which means that the directionality of a tie is only one way but not another. And you have over 5,000 null dyads, meaning that that is a null dyad, for instance, right? So there's no non-existent one. Another thing that you may be interested in looking is the reciprocity within the network, and we need to ignore the loops. Maybe not that relevant for this network particular, but something to remember. So that would counting reciprocity within the network. the ratio of reciprocated dyads is done through the command called reciprocity. So we're going to run that command over the fake Desert High School data that's an iGraph object, ifdh, and it gives us a number of 0.41, and you can check out what reciprocity stands for if you don't remember, and it will tell you that this is a measure that defines the proportion of mutual connections in a directed graph. It is most commonly defined as the probability that the opposite counterpart of a directed edge is also included in the graph. These metrics are interesting when you compare several networks to one another, because it gives you some sense of how often you have basically mutual dyads. Another feature that you may want to calculate is assortativity. We talked about it in the extended notes for Module 1 and also for Module 2, but we are going to run question mark with assortativity command to see what it does. And so when we run question mark assortativity, we see that this is a coefficient that shows whether vertices or similar vertices, based on some kind of property that we have defined, that they tend to connect to each other. And if the assortativity coefficient is negative, it means that they're not likely to connect with one another. What that actually means is, for instance, a special function called assortativity degree looks at whether vertices with a lot of degrees tend to connect with other vertices with a lot of with a high degree, right? With a high number, with a lot of ties. So just to demonstrate that, this command, assortativity degree, is run over Desert High School network, and we also specify that the network is directed. And so we see that the assortativity is pretty low, which means that in this case we know that the nodes are students, so students with high degree have well, to some extent, but pretty low extent, connect with other students with high degree. We may also want to see whether that students, for instance, with high grades connect with other students with high grades. To do that, to run a assortativity function to define that, we first need to create an object called grade, which is going to store a vector of student grades that we have within the Desert High School data. So let's create a separate object called grade that is going to look at the, just to store this attribute. So just to remind you what this looks like, right? And then the actual command would look like this. So assortativity function over a Desert High School iGraph object, and we want to look at the assortativity based on a property called grade. And the second property, so one node will be looking at grade, and the node category defining the second node is also going to be grade. That's why we specify null, otherwise we would have put a different category here. And if we wanted to do that, we would need to create another object like grade. And then we specify that the network is directed. So now we're going to run this to see, and it's actually quite high. So we can see that 0.81, and basically that is pretty, it means that students with high grades tend to connect with students with high grades to a large extent. And we know that that isn't quite true for the number of connections they have with one another overall. Right, we can compare that assortativity based on the grade for the Magnolia High School. So we're going to create another object called grade, which is going to replace the previous object called grade. If you do that, same thing. So we take a vector of the vertex attribute called grade over the other network, not the one we used before, but the Magnolia High School. So we just first create this object so that we can then run function of assortativity over the Magnolia High School network looking at the grades that are assigned to nodes, and the network is directed. So we run that for Magnolia High School, and we see that this is actually much higher at Magnolia High School network